Today I will be talking about const and immutability. So what do developers use const for in C++? Well, if you asked a sample of developers, they might look at you, smile, and say immutability. Great, everyone's on the same page. But what does immutability actually mean? Conceptually, it means that things do not change. Well, if I don't want to be abstract about it, what things am I talking about? If I asked the developer exactly to what extent do things not change, the smile would quickly get wiped off their face. They would divide into two groups. One would say shallow and one would say deep. Well, what does this mean? So if we're talking about a method and talking about an object, for example, say we have an object O with fields A, B, and C. If we're talking about shallow, that means that nothing will change directly to the fields. That is, A, B, and C will not change. If we're talking about deep immutability, that means in addition to the fields not changing, nothing will change through the fields. So you can't dereference A and then change something else. Everything in the yellow boxes here will be protected from any changes. So what does const indicate? So const is a type qualifier that C++ developers can use to specify immutability, and it indicates shallow immutability. So that means in methods, changes cannot happen directly to the fields of this, and if you have a const reference, changes aren't supposed to happen through that reference. Now, if we go back to our developers knowing this initial definition of const, the developers that wanted shallow will be very, very happy. The developers that wanted deep are now deeply sad instead. Now let's go to the other part of immutability. The change part of things do not change. What does that mean? Well, if we ask our happy developers, again, smiles wiped off their face, and they divide into two groups. One says bitwise, one says logical. Well, what does that mean? I'll be using this as a running example through the rest of the talk. Say you have a class C with a getValue method that has a const on it, which means that if I call this getValue method, I should not be changing the C object that I used to call it. So what does bitwise mean? Well, bitwise simply means no writes occur, and this is what const means by default. So this means that const is supposed to mean shallow bitwise immutability, which means no writes happen to a field. So if in my definition of getValue, if I had a field called value and I tried to write to it, the compiler would give me an error, not allow me to do this, and therefore const would mean shallow bitwise immutability. So this is a concrete example of our getValue that obeys shallow bitwise immutability. So the key assumption we're just going to make about our long calculation function here is that it only reads fields. So if that function only reads fields, this entire method will just only read fields. Logical immutability, on the other hand, has writes. The only promise logical immutability gives you is that there's no observable changes, which is a much more abstract concept. So if we go back to our developers, now that we know const supports shallow bitwise immutability, and that's it, one developer is happy and one developer is sad. So can we make this logical developer happier? Well, C++ is all about choices. So C++ includes this keyword called mutable. What mutable allows is for you to write a field in a const method. So if you have a field, you just slap on immutable, and now the compiler won't prevent you from writing to it. Again, C++ is about choices. So within our getValue definition, since we have mutable on the value field, we would be allowed to write over it. The compiler would just happily allow us to do this. While since we don't have immutable in the cache field, the compiler would prevent us from doing this. So let's go back to our example of bitwise immutability that only reads. Say a developer went along, profiled their program, and found this was one of their big bottlenecks. Can developers improve performance without ruining this meaning of const, or some meaning of const? Well, a common way to increase the performance of that is to do something like caching. So this is an example of that program just using caching instead. So in the definition of get value, I add two fields, a field that tells me if my cache is valid and space for the actual cache value. If it's not in the cache, all it does is write the value to the cache, indicate that the cache is valid, and then just returns the cache value. So in this case, writes are happening, but there's no observable difference from the point of view of the caller, except that there's better performance. So since now we know that C++ includes this great mutable keyword, both developers are kind of so-so. The developer that wanted shallow bitwise immutability has it, but they're not guaranteed it. If they see const on a method, they don't know whether or not it actually contains a write, and the developer that wanted logical can express himself, but kind of opens the floodgates by having this mutable keyword. So the overall landscape kind of looks like this, and we'll be continuing with this story. So just as an aside, just to show that const doesn't enforce deep bitwise immutability, I can take my caching example as I had it before, except this time all I'm doing is I'm changing the fields from values to be pointers, and if I just dereference them before I write to them, the compiler will happily accept this and not make me have an additional mutable keyword. Well, we want to see the caching writes in both these cases, so what we do is we want to see any deep violations as well. We don't care if the fields are references or values. It doesn't really matter to us. We get this more restrictive deep immutability, so we see more reports, and we're allowed to see what developers are actually doing. So here's our landscape as we have it right now. The developer in the middle has been very, very quiet. And everybody's been anticipating what he's about to say. Well, he wants to make one change. Oh God, he sends everyone into an absolute panic as he just cackles. Well, you're allowed to do this. So take this as an example. You can write the developer may write some method here that's just unrelated, and all it does is write the value 42 to the value field. Now, the developer is allowed to do this because in order to implement the caching example, he had to use the mutable keyword. The compiler won't do anything here to prevent them from doing this. Now, if we're assuming the return value of our getValue method is used as a hash, and we had something like this, so we declared a const C, which means the C object shouldn't change through this reference, and we're only using it through this reference. If it was in a hash map, initially, you expect anything you do to it, it will remain in the hash map. But in this case, assuming that the value isn't 42 initially, if we call the unrelated function, then the C is no longer in the hash map, which may send some developers into a panic. Just as another aside, again, C++ being about choices, there's a third way to remove const, and that's through use of the const cast. So it just allows you to remove const anywhere in the program, whenever you like. It's intended to work around misqualified libraries, but it can easily be abused. So now that we got the background out of the way, we want to say what we're actually doing. So what we do is our analysis tracks const as being deep bitwise. So we want to see any writes to fields and through fields. And if you have a const reference that actually violates deep bitwise immutability, we want those writes reported. And this is what we refer to as writes through const. With all these writes through const, we take them and manually classify them as being logically immutable or not. This allows us to observe how developers are actually using const in practice. And just a note for the rest of the talk, instead of saying not logically immutable, I just say incorrect from here on out. So going back to the developers, knowing that we observe writes, we won't be able to see the case, any of the bitwise immutable case. So anything we're going to see is going to fall in one of these categories since a write is occurring. Our goal is to just classify the write into being one of these three cases. So the first research question we wanted to answer is, do developers write through const in practice? We found emphatically, yes they do. We observed 17 unique cases in our experimental evaluation. How do developers write through const was the next question we asked ourselves, and we found that equally they violate shallow immutability, that's through using the mutable keyword, which allows them to write directly to fields, and also deep immutability by transitively going through pointers, since C++ doesn't disallow this. And of our 17 unique cases, we found 8 fell into both of these categories. The final and most important question we asked ourselves is, why are developers using const? Like in the example I showed before, the conventional wisdom that everyone kind of has is that buffering and caching is a perfectly valid reason to write through const. What we found, however, is that around half, or 9 of our 17 cases, actually had observable changes, which we classified as being incorrect. All right, so our tool we wrote is called Const Sanitizer. It's a dynamic analysis tool. What it does is it takes your normal, as part of your normal compilation process where you go from source files to object files, our tool just, as part of the compilation process, adds extra instrumentation. When you go to the linking stage from object files to your executable, we add a runtime library giving an instrumented executable. Whenever you run this executable, it will generate a report giving you all the writes through const. Now, how does our instrumentation do this? Well, for every single variable in the program, we give it what we call a shadow value. A shadow value is basically either 0 being non-const or 1 being const, and this is a simplified version of our analysis. For more details, see the paper. But basically what our analysis does is preserve const transitively, so it gives us this deep bitwise immutability reasoning. So if we go back to our running caching example and see how our shadow values work, if we have a const c, lowercase c, our analysis would instrument this, giving it a shadow value of 1. Then if it later called getValue, the constants of this would be passed through thread local storage, so we don't mess up calling convention or anything like that. And since this is const, we know that both of its fields should be const if we have deep bitwise immutability, and they both get assigned 1 as their shadow value. Now, if the program dynamically executes either line 3 or line 4, which is the write to value or cache, given that the shadow value is 1, our analysis will generate a report. This is what our report would look like. So it would report the write to value on line 3 and the write to cache on line 4. So initially, we had a hypothesis as to why developers would use logically immutable, and this is what we call attributes. So valid and invalid reasons for writing through const. Initially, we thought buffering and caching. We also thought of delayed initialization, so lazily initializing a field when you use it, or simply being incorrect. And there's some additional attributes included in the paper, but these are the main ones. So we ran our experiment on 7 C++ projects. These were a selection of the top projects on GitHub that were actively maintained and had a pretty active user base. They ranged from Google's Protobuf serialization framework, which was over 200,000 lines of code, down to Mosh, which is SSH alternative at 13,000 lines. Now what we did to evaluate these projects is we compiled them all with our Const Sanitizer tool, and ran the provided tests, or if it didn't have tests or was an interactive program, we just simply ran the executable. This generated a report with a bunch of writes, and then we classified the static locations of these writes, and we classified the location of the writes. Our classification consisted of a root cause, so how the write occurred, and an attribute, why the write occurred. So recall that if the reason is mutable, it's because they wrote directly to a field, and if the reason is transitive, that's because they were writing through a field, and that's a violation of deep immutability. So the first thing we're going to look at is Protobuf. Protobuf had a large number of dynamic occurrences, over 100,000. In this case, we manually grouped all the static locations. So if you think back to our caching example that needed 2 writes to implement caching, we would group both of those together as one entry in this table. So two of the writes we found were incorrect. That is, they weren't logically immutable at all, while 3 of them is kind of something we expected, buffering or caching or delayed initialization. So here's an example of caching. So in the ellipses up there, the method computes the total size, and at the end of it there, it writes to a cache. So this would make the developer who wanted shallow logical immutability quite happy, because this is what that follows. Protobuf, however, also modifies a linked list through a const reference. So if that P there has a const, and what that const means is the node should not change. The second line, that while loop, just iterates over it. That's fine. And the final line there, it writes to the next field of P, which definitely changes the linked list, which would be very unexpected if you weren't expecting it. We think this happens because conventional advice you get from C++ developers is to use const wherever possible. In this case, the developer could slap a const on there because the next field was mutable. They didn't really have to, they may have not actually thought about immutability, they just put it there because they could. Now, next we looked at LevelDB. In LevelDB, we found half the cases were incorrect, while half the cases were logically immutable. But the interesting thing here is we found a new attribute we didn't think of going into this, and that was unit testing. So what unit testing looked like is something like this. This class only exists as part of the unit testing framework. So the counting file extends a class that's only in production code and overrides the read method to add a counter. This counter just counts how many times this method was called, so that the testing framework can ensure that it's only called a certain number of times. And this is fine because in normal code or elsewhere in the code, you can't access the counter variable, and there's no observable difference to this write. And this would make the deep logical immutability developer happy, since in this case they're going through a field. Now, with the remaining projects, the majority of them, that is 4 of the 6, were not logically immutable. So for an example of that, first we'll look at fish shell. This one simply removes the constant writes. So this get_opt internal helps in handling command line arguments. The const up there should say that the order of the strings in the array should not change. Then it casts away the const to call an exchange function. And what does the exchange function do? Well, it changes the order of the strings, therefore violating that const and your expectations. So we contacted the developers, and this was actually fixed by the developers. The funny thing about this is I was watching their initial response, and their initial response was, what are you talking about? The const applies to the content of the string, so it's correct. So this is fine. And then they quickly deleted that comment. It's like, oh no, you're right. And to fix it, they just removed the const and removed the const cast, and everything was great again. And finally, Mosh just wrote directly through const, so it got this parser object as an argument, and then immediately wrote to one of its fields. It was allowed to do this because the field was public mutable. We contacted developers, and they're like, oops, sorry, we'll fix that. To fix it, apparently this field only existed as part of when it was being prototyped to make sure they were actually handling all the cases. It was just left over and they just simply deleted it. So relating our work back to our research questions, we found that yes, developers do routinely write through const. They violate shallow and deepwise immutability equally. And around half of the writes through const we found were not logically immutable. And this appears to be undesirable since developers actually fix them. So parting words, I'd like to invite everyone to try it out. All the code's available on GitHub. I don't expect anyone to spell my last name. So you can click through on eyl.io, and those are the repositories. And last remark, I'd just like to thank Derek Rayside for helping improve the presentation quality. Thanks.
So we have time for questions and student volunteers to give you microphones since we're recording.
So, indeed, C++ doesn't do deep immutability. So what you're testing for isn't what you get from const anyway.
Yeah.
Did you report any issues that were issues of that form? And if you did, how did developers react to that?
So most of them didn't respond to it. Developers don't actually seem to care that much, oddly enough. It seems like they're initially, like, it should mean deep is kind of the intuition most people get. So that seems to be what people kind of follow.
Is a good idea, because people in Java were trying to do deep immutability, etc.
Yeah.
So what do you think?
Yeah, so the question was, what do I think about const in general? So I think const has way too many meanings. If they actually stuck to just one, that'd be great. Then people could actually understand it. Right now, it's kind of just like a wild west. If it just meant the least restrictive one, which is deep logical immutability, at least developers could depend on that and actually exploit that in a way. Like, they know that they won't be able to change anything observably through a reference.
So I was going to ask a question I think you've already answered, which is, were there any C++ programmers in the room? How would you advise them to use const? Or would you just say, just forget it, that's the C++ way of doing things, just...
Advice would be, make sure it actually means something, don't just add it because you can.
So use it only if it means deep logical immutability.
Yeah.
And
make sure it
means deep logical immutability.
Yeah, make sure it at least means deep logical immutability. Otherwise, it will be very confusing.
Does that piss off some of the other developers that were on the bottom of this slide?
It might. It's kind of muddy in that way aside, it kind of gets confused with thread safety, oddly enough, and it's kind of a mess.
So really your advice would be use Rust.
If only.
So on that basis, let's thank John. Any other last questions? No, bye.